So today we're going to look at two theorems, Stokes' theorem and Gauss's theorem. First we're going to look at Stokes. So Stokes' theorem is essentially the parent theorem of Green's theorem. It's an extension of Green's from 2D to 3D. Recall Green's theorem turns a single line integral around a plane boundary curve into a double integral over a plane region D. This is Stokes' theorem. So you see how you end up evaluating the integral of the curl of vector f. Whereas Green's theorem deals with finding the area of a plane region D, Stokes' theorem deals with finding a line integral around the boundary curve of a space curve S. So as you can see, Green's theorem basically just satisfies one specific instance of Stokes, since it's dealing with 2D, so z is 0, so partial z partial x is 0 in 2D. Green's theorem is only applicable to closed regions, and the same goes for Stokes, except in 3D. So before we launch into full-fledged application problems, we first need to get familiar with the process of parametrizing a surface, which is a core step in these types of problems. Let's take a look at number 4 on the test review sheet, which will introduce us to the process. So this problem is asking us to give a vector description or parametric representation for the sphere having radius 3 and centered at the point 1, 2, 3. So this problem wants us to give a parametric representation of this given sphere here, which will ultimately take the form of a vector. Right now we're dealing with 3 variables, x, y, and z. And here's the equation of the sphere. It's not centered at the origin, so we need to take the center coordinates into account when we parametrize. So if we recall the spherical parametrizations, it's x becomes rho sine phi cosine theta, y becomes rho sine phi sine theta, and then z becomes rho cosine phi. Except in this case, when we have to take the center into consideration because it's not at the origin, so it's actually this. The problem gives us rho, or the radius, which is 3. So once we reorganize these equations to just represent x, y, and z, we have our final parametrization. So if we go to the visual here, the graph, we can see that this horizontal band latitude here is representational of where phi is constant, and then this vertical band, or longitude thing, is where theta is constant. So by parametrizing the surface, we've changed from 3 variables, x, y, and z, to just 2 variables, theta and phi. Now that we are familiar with the finer details of how to parametrize a surface, the next problem we'll take a look at is number 10 from 16.8 in the textbook, in which we'll apply the parametrization we just discussed, and also take a look at Stokes' theorem. So problem 10 gives us vector f, and a curve C, which is formed from the intersection of a plane and a cylinder, both of which are given. And the larger problem here is we're asked to use Stokes' theorem to evaluate the single integral over C of vector f dot dr. And it's also given to us that C is oriented counterclockwise as viewed from above. So this is what it looks like visually. It's a plane going through a cylinder, forms this oval here, and then we can see C as the boundary going counterclockwise around here, and then S being the oval that was formed. So with what this problem is asking us to do, it'll be easier to solve it with Stokes' theorem, which I'll demonstrate in a bit why that is, but we'll also walk through this problem both with and without Stokes, essentially, so we can verify the theorem. While also understanding how it's easier to apply Stokes to solve this. So here's Stokes' theorem written out again. And let's do the double integral first, since this is the application of Stokes, which turns it into this double integral. Our first step is to find the curl of vector f, which is the cross product of the original vector and the vector differential operator, also known as del. So here we'll just plug and chug. So this matrix multiplication turns into this extended form. So we need to find some partial derivatives. So p, q, and r are just taken from the given vector, and note that Z is also given in terms of Y, so we can sub that in later, but for now, let's just find the partials in terms of X, Y, and Z. So now that we have our relevant partial derivatives, we just plug them in and get our final result, our curl. And now we can rewrite this vector subbing in the y plus 2 for z like we talked about earlier, so that it's just in terms of x and y. Now we're still missing ds, which can also be written as rx cross ry dA, and we'll find that first by parametrizing our surface, so we can end up finding the normal vector. There is no parametrization given, so we can create our own by taking what's given in the problem. We have z equals y plus 2. So we can simply parametrize this as x equals x, y equals y, and z equals y plus 2, which gives our parametric vector r. Next we'll take r prime x and r prime y, I'll just call them rx and ry like before, and we'll cross them to get our normal vector. So now we'll just bring these two vectors back into the integral and notice that it's now dA instead of ds, and the double integral is over d instead of s, d being the projection of s onto the xy plane, which is just a circle in this case. So now just dot the vectors and do the math and end up with the double integral over d of y plus 1 dA. So this dA needs to be replaced. And at this point, since we have a x squared and y squared we're dealing with at the problem, it's easier to convert this double integral into polar to solve from here. So recall when we're doing polar, x is r cosine theta, y is r sine theta, and just put in the appropriate bounds. R is going from 0 to 1 because the radius of the cylinder is 1, and then r dr d theta. So now we just have to solve it out. This is just your regular old double integral calculation, and I'm just fast forwarding and cutting so you don't have to watch the entire thing. But we do end up with our final answer of pi. So now let's go back and do the problem with the single integral instead of the double integral to verify that Stokes' theorem indeed holds true and to compare the problem-solving processes. Now we're doing the single integral over c of vector f dot dr. So since this is a single integral this time, we have to find a vector r that has only one variable and not two like we did last time. Since the given surface is a cylinder and the projection is a circle, the best parametrization to use here is setting x as r cosine t and y as r sine t. And in this case the radius is 1, so we just have x equals cosine t, y equals sine t, and we're given z equals y plus 2, so we can set z as sine t plus 2. And because we're dealing with the surface rotating around in a full circle, so to speak, full rotation, the bounds of t go from 0 to 2 pi, which is just one full rotation. So here is our r vector, and r prime is just negative sine t, cosine t, cosine t. So this is what we're dotting with vector f. So then of course now we replace the components of vector f with the parametrized versions, bring them under the integral, which note is now bounded and in terms of t, and dot them. So now you see from this dot product slash integral result here that this is a much more complex integrand than what we had to deal with when we just used Stokes. So let's solve it anyway by splitting it up into multiple integrals, and I'll color code them so it's easier to tell the integrals apart. Alright, so obviously now we just have to solve all of them out. And ultimately we're going to add them all together to get our final result. So I just sped through this part because it took a while. I also could have kept some of the integrals together. I basically split them up into the most possible number because I thought it would be clearest this way. But notice how some of the u-subs are the same, so you could have kept a few of them combined and it would have led to the same result. So now when we add them together, we also get pi as an answer, which is equal to the answer we got using the double integral. So therefore we verified the Stokes theorem, and you can see that it is a much more elegant solution in problems like these to apply Stokes instead of just using the single integral. Okay, so moving on, the second theorem we're exploring today is Gauss's theorem, which is also known as the divergence theorem. Gauss's theorem relates a double integral of vector f over a space curve S to a triple integral of the divergence of vector f over a simple solid region E. In this case, S is the boundary surface of E with outward orientation, and E has to be a simple solid region. This theorem states that under conditions that fill this applicable criteria, the flux of vector f across the boundary surface of E is equal to the triple integral of the divergence of vector f over the region E. Now let's look at an application of Gauss's theorem in number 11 from the test review sheet. So this problem wants us to find the flux of this given vector function outwards through the surface cut from a paraboloid by a plane. So let's just draw it in here. It's just a paraboloid along the positive z cut off by z equals 1. And let's write Gauss's theorem here so we can see it. Now let's apply Gauss's theorem first. So we're doing the right-hand side here with the divergence of vector f under the triple integral. We can use this formula to find the divergence of vector f. So again, we have to find some partial derivatives here, as is given by the problem p equals 4x, q equals 4y, and r equals 2. So we just find the right partial derivatives, and we'll plug it in, and we get 8. Then we'll bring this back under the integral, and now instead of writing dv, we need to find bounds for our integral. So since we have a paraboloid, it'll be easiest to use cylindrical coordinates. So we'll have dz, dr, d theta. So now we just solve it out. And again, I'm going to speed through this part. You know the drill. It takes a bit of time. And we end up with 4 pi as our answer. Now let's do it with the double integral and compare the processes and see if we get the same answer. Recall that S here is a boundary surface of E, which is this whole paraboloid thing that is given in this problem. It has to be closed in order to apply Gauss's theorem, and a paraboloid is not closed. It extends infinitely upwards, but in this problem it's closed by the plane z equals 1. This theorem also requires that the surface has a positive or outward orientation. So what we need to do here is assume those conditions, split this given paraboloid and plane into their two respective surfaces, calculate the vector surface integral of both, and then add them together to get our final result. So let's call the z equals 1 plane S1 and the paraboloid S2. S1 can be parametrized as x, y, 1, the 1 coming from z equals 1, and then from it we take rx and ry, cross them, and get our normal vector of 0, 0, 1. At this step, we need to make sure the sign or direction of the component matches with our assumed conditions. Right now, we need all surfaces to be oriented outwards, which means the z component or the k component should be positive, which it is, so we're good. Now let's rewrite the whole thing under the double integral. Once again, the ds has changed to a dA, which we can replace with polar and solve it out to get 2 pi. There is also a slightly faster way of getting to this answer, because after we dot the two vectors under the integral, we just get 2. And we have a dA here, which is the area of the projection of S1 onto the xy plane, which is pi. It's a circle. So we'll just get 2 pi as our answer simply by multiplying them. Now let's move on to S2. S2 can be parametrized as x, y, x squared plus y squared. And from here we can do the same thing. We take rx and ry, cross them, get a normal vector of negative 2x, negative 2y, 1. At this point, we need to check again that the signs line up with the orientation, which in this case they don't, because with the paraboloid and the parabola, the vectors are oriented downward. And it's a little bit harder to see than with the plane, so I'm just drawing it out for some visual intuition. But yeah, they're all oriented downward, which means the k component of the normal should be negative, so we're just going to fix that by negating the vector. Then we'll bring it under the double integral again and dot it with vector f, again switching out the ds to a dA, and then we can convert this to polar again. So we have x squared plus y squared equals r squared, and we'll take it from there. And we end up with 2 pi. Now all we have to do is add S1 and S2 together to get S, so 2 pi plus 2 pi equals 4 pi, which is the same answer as we got when we used the triple integral. So nice, now we've also verified Gauss's theorem. And now we know how to use both theorems in application.